Welcome to our next video in the series on condensed material. In this video I want to talk about the band structure of manganese oxide. Manganese oxide forms a rock salt crystal structure, which means that we have alternating manganese and oxygen atoms on a cubic lattice. It's like checkerboard order in 3 dimensions. And in order to understand the basic electronic structure, we can start with the periodic table, where we have oxygen atoms and manganese atoms. And the manganese atoms turn to plus, getting the configuration of neon, so a filled shell. The oxygen atoms become 2 minus and also forming a neon filled shell like configuration. So based on the ionicity of your atoms, you should expect this to be an insulator of a filled oxygen shell. So we have 6 bands, or 3 if you look at spin degeneracies, and those are filled, and then the Mg oxygen or MgS bands should be empty. And indeed, if we do a density functional theory calculation, we find here 3 bands in the range from -7 to -2 eV of oxygen to P character that are completely filled. And then we find the manganese S character at higher energies to be empty. So here we see the band structure. I turned the oxygen to P character red, the manganese 3S character blue, and we also see the total densities of states and partial densities of states, the total densities of states in gray, the oxygen to P densities of states in red, and the manganese 3S densities of states in blue. So our occupied oxygen to P orbitals are not fully of oxygen to P character. There is some manganese 3S character in there that is responsible for the bonding. You are covalent bonds between them that make your crystal stable. And then we see the manganese S character coming up here, or the total loss, and then the manganese S character in there. So if we look at the bands of the oxygen to P character, so we zoom in to that energy window and compare this with the nearest neighbor tight binding model, then you see that all the basic features are there. There is some higher dispersion for some band that is not reproduced on a nearest neighbor tight binding model, but that is okay. You have some longer range interactions here, especially in a cubic lattice. You have an interaction on the diagonals that is not negligible and needs to be included in your model and is not here to get also those dispersions right. But everything is local and short-ranged. So as we've seen before, we have our manganese atoms and our oxygen atoms, and we can look at the manganese S orbitals and the oxygen P orbitals to see if we can understand what our states are. Well, the manganese 3S is much bigger than the distance between the oxygen and the manganese atom, which is okay because this orbital is going to be empty, so it doesn't really matter if this is non-zero at the nucleus. The thing is not occupied anyhow. Then we have the oxygen to P, and now you see that the oxygen to P is basically also determining the distance between the atoms. The moment you move in your manganese atom, you have to make a deformation to the oxygen to P. You have to mix in a 3P orbital. That costs energy, so you don't want to move too close. And these are then your atomic basis functions. We can now make Wannier functions. And now you see that I made sure that I have nodes at the nearest neighbor atoms, and the same for the oxygen to P wave function. And these wave functions are now nicely orthonormal to each other. Yes. So it is those functions that we use as a basis state, where the oxygen to P is basically atomic like and occupied. The manganese 3S, well, has a lot of atomic features, but also, especially further out, is pretty deformed. But that's okay, because the thing is not occupied, so it's okay that it goes to higher energy. And these are then the three-dimensional plots that we have. So the manganese, or the oxygen 2p, is not perfectly local. There are some tails on the manganese atom, but it's all within range. And the oxygen, or the manganese 3s, in principle should be much larger, but well, you have to have a node at the nearest neighbor atom. And with these orbitals we can look at the bands. The occupied bands, of course, are exactly represented, because that's how we constructed our wave function. The unoccupied bands, here we have the problem that there are more bands in the basis than bands that we put in our Wannier function basis, so you have to make an approximation. If you want these bands to be represented better, we have to put in the manganese 3p as well, and also higher energy orbitals. The 3d is coming into play as well. But those orbitals are unoccupied, so they're not so important for total energy or densities of states, or many of the other properties of the material. So if we now look at the atomic picture, then we have the local picture, then we have our oxygen orbitals, the 2s and the 2p. We have our manganese orbitals, the 2p and the 3s, and then we start to make interactions between them. We get the bonding and the anti-bonding state. It is the bonding states that are occupied and the anti-bonding states that are unoccupied. And these correspond to the red bands and the blue bands that you see there. So where a single atom would just make a single bond state, in a solid you get two bands that are the occupied oxygen 2p-like bands and the unoccupied manganese 3s-like bands. So I hope to have shown you a little bit how these kind of band structures work in real materials. That indeed the occupied bands are very atomic-like. For the unoccupied bands, of course, you are able to make deformations. It doesn't cost you any energy anyhow to make changes in those orbitals, as they are not occupied. Thank you very much for your attention. We see each other in the next video. Stay healthy.